Assalamualaikum. For this project, our selected petroleum product is lubricating oil. Petroleum chemistry is a branch of chemistry that studies petroleum products, hydrocarbons, refining processes, and their application in industries. Petroleum products include fuels, lubricants, and petrochemicals that are important in daily and industrial use. Lubricating oil is used to reduce friction and wear between moving mechanical parts, helping machines and engines to operate more efficiently. It mainly consists of base oil, hydrocarbons, and additives that improve lubrications in performance and stability. Lubricating oil is widely applied in automotive engines and industrial machinery to protect equipment from damage and overheating. So in this project, lubricating oil was analyzed using FTIR and GCMS techniques to identify its chemical composition, functional groups, and hydrocarbon compounds to evaluate its quality and performance.
Chemical component of lubricant oil consists of two sections, which are base oil and chemical additive. In the base oil, it has two base, which are mineral base, which contain paraffin, naphthalene, and aromatic, while synthetic base consists of polyalpha olefin, ester, and polyalkylene, while the chemical additive consists of two main additives, which are tribo improver and maintenance. Trivo improver focus on surface protector, which consists of anti-wear and extreme pressure agent and zinc dialkyl diatophosphate, while the maintainer, which are oil life extension, consists of detergent and dispersion. To maximize machinery lifespan and lower operational costs, a high-quality lubricant oil must balance an adequate viscosity index, have high oxidative stability, and have strong demulsibility.
Lubricating oil is commonly used in automotive engines and industrial machinery to reduce friction, minimize wear, prevent corrosion, and dissipate heat during operation. Lubricating oil also contains various chemical components such as paraffinic hydrocarbons, naphthenic hydrocarbons, aromatic compounds, and antioxidant, detergents, anti-wear additives, viscosity modifiers, and dispersants. So we use FTIR and also GCMS machine. For the sample preparation, FTIR, the lubricating oil was analyzed directly without extensive pretreatment. A small amount of oil was placed directly on the ATR crystal surface because FTIR allows rapid characterization of liquid petroleum samples with minimal preparation. For the GCMS, the sample was diluted using hexane to reduce viscosity and improve injection efficiency. FTIR analysis was carried out to determine functional groups and molecular bonding characteristics present in the lubricating oil sample. The analysis was performed using an FTIR spectrometer equipped with an ATR, which enables direct analysis of liquid samples without extensive preparation. Before analysis, the ATR crystal surface was cleaned using ethanol and lint-free tissue to avoid contamination. A small drop of lubricating oil was then placed directly onto the crystal surface and the spectrum was recorded within the range of 4,000 to 400 cm. Alkene CH stretching vibrations 2,850 to 2,960 indicate saturated hydrocarbon chains, while aromatic C double bond C vibrations 1450-1600 cm suggest the presence of aromatic hydrocarbons. Additionally, carbonyl C double bond O peaks around 1700 to 1750 cm indicate oxidation product or ester additives, whereas hydroxyl OH absorption bands 3200-3600 cm may suggest moisture, contamination, or oxidation. Sulfur and phosphorus-containing compounds such as ZDDP additives were also considered due to their anti-wear function. GCMS analysis was conducted to determine the chemical composition and hydrocarbon constituents present in the lubricating oil sample. The lubricating oil sample was diluted with hexane to reduce viscosity and improve injection efficiency. Approximately 1 microliter of the diluted sample was injected into the GCMS instrument using a microsyringe or automatic injector. During analysis, compounds were separated in the gas chromatograph according to the difference in volatility, boiling point, molecular size, and interaction with the stationary phase of the column. Lower molecular weight compounds eluted earlier, while larger hydrocarbon molecules required a longer retention time. After separation, compounds entered the mass spectrometer for ionization and fragmentation. Identification was carried out by comparing the mass spectra with the NIST spectra database based on retention time, fragmentation pattern, and similarly indexed values. TCMS commonly detects linear alkenes, branch hydrocarbons, cycloalkenes, aromatic hydrocarbons, and additive derived compounds in lubricating oil.
Next, moving on to FTIR analysis of unused lubricating oil. The most prominent peak that can be observed is within the range of 2921 per centimeter to 2854 per centimeter, which attribute to the asymmetric stretching vibration of methylene group and also the methyl group. These bands are characteristic of aliphatic hydrocarbon chain and are commonly present in both base oil and additive component of lubricating oil. As a result, they are consistently observed in the spectra of unused lubricating oil sample. Next is the peak at 1698 per centimeter, which attribute to the stretching vibration of carbonyl group. Since the sample used is unused lubricating oil, the presence of this band is likely associated with oxygen-containing additive or ester-based compound rather than the oxidative degradation product formed during engine operation. Lastly is the peak at 1457 per centimeter, which indicate the bending of methylene group. The presence of this peak further confirms the dominance of aliphatic structure in lubricating oil formulation. Next, the absorption peak observed at approximately 1360 per centimeter is attributed to sulfonate group, which is sulfonate-based detergent in a lubricating oil. Next is the peak at 1292 per centimeter, which is the stretching vibration of CN and C double bond N bond in polyaniline. It also reported that the peak at approximately 1292 per centimeter correspond to the CN stretching vibration in Pani, confirming the presence of amine group in the polymer backbone. However, to the absence of the characteristic benzenoid and quinoid band around 1477 per centimeter and 1569 per centimeter suggests that the detected peak is more likely related to lubricant additive component. Next peak is observed at 1197 per centimeter, which is the sulfonation band of calcium sulfonate detergent additive. When the concentration of calcium sulfonate detergent additive is high, it results in a sharp and distinct absorption peak at 1197. However, as all degradation progresses, a new broad peak emerges and increase in intensity at 1150 per centimeter. Lastly is the observed peak at 1007 per centimeter, which is the stretching vibration of the phosphorus oxygen carbon POC linkage presence in the ZDDP molecular structure. The POC bonding in ZDDP typically appears within the 1090 to 920 per centimeter in the spectrum. The presence of strong absorption at 1007 per centimeter indicates a high concentration of active and unspent ZDDP anti-wear additive.
For the GCMS analysis, the chromatogram revealed a total of 30 peaks indicating the presence of multiple chemical constituents. The identified compounds mainly include long-chain hydrocarbons, fatty alcohols, terpenoid compounds, and minor aromatic constituents. The chromatogram was dominated by long-chain alkenes such as henacosane, heptacosane, dotriacontane, pentatriacontane, tetracontane, and tetrapentacontane. Among these compounds, pentatriacontane was identified as the major constituent, showing the highest peak area percentage of 9.64% at a retention time of 23.886 minutes. Other abundant hydrocarbons included tetrapentacontane with 6.50%, dotriacontane with 5.39%, and heptacosane with 4.28% peak area percentages. The presence of these long-chain saturated hydrocarbons suggests that the sample contains waxy lipid components and hydrophobic metabolites. These compounds are commonly associated with plant cuticular waxes and natural product extracts. In addition, several fatty alcohol derivatives were detected, including 1-decanol-2-hexyl and 1-hexacosanol. The repeated detection of 1-decanol-2-hexyl throughout the chromatogram indicates that it may be an important constituent of the sample. Fatty alcohols are known to function as emulsifiers, thickeners, and stabilizers, contributing to the texture and stability of products. Another important compound identified was squalene, which accounted for 6.72% of the total peak area at a retention time of 28.513 minutes. Squalene is a naturally occurring triterpenoid compound recognized for its pharmacological, chemopreventive, and therapeutic properties. Therefore, its presence may indicate potential bioactive or therapeutic value in the sample. The analysis also identified 2H-pyrene 21,5,6-dihydroxypentyl, which belongs to the lactone group. Lactones are often associated with antimicrobial activity and may also contribute to aroma and flavor characteristics. Lastly, most compounds eluted between 20 and 32 minutes, indicating the presence of relatively high molecular weight and low volatility compounds. The predominance of these late eluting compounds further confirms that the sample mainly consists of nonpolar and lipid-like substances.
In conclusion, FTIR analysis was carried out to identify the functional group and additive present in the lubricant. The results show the presence of aliphatic hydrocarbon, carbonic compounds, surfactants, detection additive, and phosphorus-containing anti-wear additives such as ZTDP. These compounds are important because they help improve lubricant performance, thermal stability, and wear protection of the engine components. Next, GCMS analysis was used to identify the hydrocarbon compounds in the lubricant oil. The analysis detects long-chain alkenes and other organic compounds that are commonly found in the lubricant formulation. The chromatogram also indicates the presence of high molecular weight and low volatile compounds, which are important in maintaining lubricant viscosity and stability during operation. We showed that both FTRR and JCMS successfully characterize the lubricant oil sample and provide important information regarding its chemical composition and additive. These techniques are very useful for lubricant quality control, additive identification, and performance evaluation.